Think of a window on a cold day. As the temperature drops, a thin layer of fog forms, and the sharpness of objects behind the glass starts to fade. You can still make out the shapes, but the fine details become increasingly hazy, almost as if the world is softly melting into itself. This is the blur effect. Today we'll discuss how blurring actually works, different kinds of blurs, and of course, how to code them. To create this effect, we'll use shaders. If you're not familiar with what a shader is, think of it as a small program that runs on each pixel of an image. It takes inputs like the pixel's color and position, then calculates and returns a new color for that pixel. We'll create this using the GLSL language whose syntax is somewhat similar to C. Let's create the initial function of the shader and return red to see if it works. Now, since this program runs for every single pixel, that means every single pixel is red, so the image is well red. Let's continue by reading the color of the current pixel and simply return it. This will display the original image as it is. By the way, if you're not familiar with those UV coordinates, they represent a percentage of the screen, indicating the position of a pixel. These coordinates range from 0 to 1, where 0 is the start and 1 is the end of the screen, in both the horizontal U and vertical V directions. So imagine an n by n grid that includes the current pixel and its neighbors, forming a n by n square. Create two nested loops that go from negative n divided by 2 to n divided by 2, which will help you cover each pixel in the square. Now, since we know where the current pixel, aka the grid center, is on the screen, we can compute each neighbor position relative to the center by simply adding an offset to the current pixel's coordinates. That offset is calculated using the loop variables I and j, and is divided by the image resolution. Dividing by the resolution turns the offset from integer pixel counts into float texture coordinates. Now we read the color of each neighboring cell and average them together, so every image pixel's color depends on its neighbors. You might notice that the greater the n, the stronger the blur is. This is called the box blur. We've imagined a grid representing the pixel the shader is currently processing, along with its neighboring pixels. The final color of the center cell depends on the colors of its surrounding pixel neighbors. In a 3x3 grid, each pixel, including the center, contributes equally to the final color. Since there are 9 pixels, each one affects 1/9 of the final color. This value, 1/9, is called the weight, which shows how much each pixel contributes to the final result. The total sum of the weights is always 1. By adjusting the weights unevenly, you can create some pretty crazy effects. You might have heard of Gaussian blur. It's a higher quality blur than the previous one, but it's also more expensive to compute. The basic idea is, the further a pixel is from the center, the less weight it has. So pixels closer to the center will have more influence on the final image. If you want a stronger blur, you can increase the grid size. To implement this in code, you can base the weight of each pixel on how far it is from the center pixel. For even better results, consider using a Gaussian distribution. This is a function that takes the offset coordinates and returns a weight. The weight increases as the pixel gets closer to the center, and decreases as the distance increases. There are ways to optimize this process, like using two shaders, one for horizontal blur and another for vertical, but for now we'll focus on simpler methods that are easier to implement and understand. As the name suggests, directional blur is related to movement. Instead of blurring pixels in all directions like a regular blur, directional blur makes it look like objects are moving in a specific direction. To implement directional blur, you begin with the UV coordinates, which are the position of the current pixel on the screen. Then you shift this position in a specific direction a couple times. In each step, the offset becomes larger, causing the blur to stretch in that direction. The rate at which the offset increases controls the strength of the blur. In code, we start with the UV coordinates, and in a for loop we begin sampling colors from offset pixels. To intensify the blur, we scale offset by a float. The more we scale it, the more spread out the blur becomes. In a radial blur, pixels near the center should appear clearer, while pixels further from the center get more blurred. This means the amount of blur depends on how far a pixel is from the center. To create this effect, we scale the offset, which is how much we shift the pixel, based on a distance from the center. You can also multiply this offset by a number to control how strong the blur is. To improve the quality of the blur, you can increase the range of the for loops. But keep in mind that increasing the number of samples will also make the effect harder to compute. Now that you've got a decent understanding of how blur works, you might as well can try implementing it on your own. And shout out to InnoGames for posting this amazing article about blurs, which I used as a guideline for this video script. You can check it out in the description. Until next time.